Yes, sir, I'm present. Yes, sir, certainly. Thank you for the opportunity. So, our next speaker is Professor Sanatan Chattopadhyay, who is currently a full time professor in the Department of Electronic Science, University of Calcutta. He was the postdoctoral fellow at the Singapore MIT Alliance during 1999 to 2001. Professor Chattopadhyay worked as a research associate from 2001 to 2003 in the School of Electrical, Electronics and Computer Engineering, University of Newcastle. Upon time UK and subsequently he was appointed there as the lecturer in 2003. He left UK and joined the Department of Electronic Science, University of Calcutta in 2007. He has also worked as a research and development team member in ATMEL UK to implement strained SI MOSFET in smart card technology. In the University of Calcutta, Professor Chattopadhyay worked as the founder convener of the Research Center for Research in Nanoscience and Nanotechnology CRNN in 2009 and still serving with that capacity. He is the founder member of the Center of Excellence, Systems Biology and Biomedical Engineering in the University of Calcutta and working as the academic coordinator. He has also developed the quantum scale material devices and digital microfluidic group, QMAT, and DGMF group in the Department of Electronic Science CU. Professor Chattopadhyay is the fellow of West Bengal Academy of Science and Technology. He has published more than 300 international journal and conference papers, co-authored 2 books and 25 book chapters and 1 patent on FinFET. His current research interests include quantum dot devices, strained SI and nanowire MOS devices, nanoscience and nanotechnology, electronic biosensors, electronic detection and monitoring of food adulteration, digital microfluidics, and solar cells. Thank you, sir, for being here, present with us in this wonderful FDP session. Sir, you may please proceed with your
Thank
presentation.
you very much, Subhra.
Thank you, sir.
And thank you very much to Gautam, Somendu, and others who has given me the who has giving me the opportunity to share this topic in this evening with a group of teachers. And hopefully, even though it is detached, and I heard that people from southern part of India is also participating. So I hope we will have a constructive discussions upon this session. And if there is any problem of hearing me or visualization, please immediately interfere me during my presentation. And it will be a almost 1 hour to 1.5 hour session. And also I like to say that it is a very short time for presenting this entire topic within this time. But let's see how much we can touch. What I am trying to deliver here is not to share my research only. Rather, it will be a one type of tutorial sharing or lecturing. I will start from the basics of MOSFETs, although I know that you know this already, but I will put a bit more uh, stress on the physics of MOSFET devices and MOS devices, and then how the physics has actually driven the entire science and technology related to CMOS to this era of nanoscience and nanotechnology, and where the MOSFET itself has been transformed from macro scale, micrometer scale, to now the quantum scale. So with these few words, now I like to request you, Can you see the screen now? No. You can see, but I cannot see. Just 1 minute or 2 minutes. I'm uploading the file. This one? Which one? File load. ঠিক আছে। Just 1 minute. I'm trying to find out my file. Can you see now this one? Hello?
No, sir. No, sir.
Now,
No, sir.
now?
No, sir. So I think you can unshare the screen and reshare it.
Okay, that is the way. So I'm
And you can share the entire window also.
Yeah, that I am doing actually.
Okay, okay.
So it is the window or the entire screen. Which should I share?
If the document is open, then you can share the screen that way.
Yeah, that I am trying actually. Now?
Yes, sir. Yes, sir. We
Okay,
can see.
thank you. Thank you. Sorry for the interruption. So it is the nanoscale CMOS. The thing I am going to touch is the entire semiconductor device as a whole, and then the roadmap of the semiconductor devices. Then I will pinpoint to MOSFET, its evolution, and the alternative routes that people are at the moment trying to develop. So the point is the invention and systematic progress of semiconductor devices have revolutionized the world of electronics, communication, control, data processing, and also the consumer electronics, because with the invention and the progress of electronic gadgets is actually changing our lifestyle as well. One of the major achievements of that modern physics is the progress and success of solid-state physics, without which it is not possible to come to this level. And particularly in the 90s and 30s, 20s and 30s of last century, the new technique of quantum mechanics was applied to develop the electronic energy band structure of semiconductor, which gave the roadway for the successive and successful discussion about the semiconductor properties, that particularly their transport. And along with that, we need to mention about the contribution of discovery of X-rays, which gave first the idea about the crystal of a material, its presence and its properties, which actually helped to implement the mathematical model to develop for the semiconductor transport properties. So the story started almost 125 years ago, say from 1900, and the devices during that time was the vacuum tubes, which actually eventually evolved on during 1947 to 1960. It was a transition, and we can also say it is the competition between two devices. One is the bipolar transistor and another is the MOSFET. And particularly the bipolar transistor, even though it was discovered first, but that was initially on germanium material. So therefore it was almost impossible to control the leakage current, and that's why people look for the alternative materials which gave birth the silicon and the so-called silicon technology. And therefore, during 1950 to 1960, it was the birth year, we should say, of this modern electronics, that is the so-called CMOS electronics, which eventually and successively led to the development of this modern CMOS technology, where we are living at the age of ultra large scale integration, where the CMOS or MOSFET dimension has come down to quantum scale, that is so called nanometer, under 10 nanometer nowadays. And if we look about the discovery of the devices after 1925, it was initially, the concept was given in 1945, and particularly Linenfeld in 1926 to 1938, he actually developed the nice mathematical model in perception of some device which has actually came out as the MOSFET in course of time. But during that time, nobody knew that that was the first concept about the MOSFET. And it was started to be conceptualized in 1945 onwards. But during this 1945, the first progress was made in the point contact of transistors, then junction transistors, then double diffusion transistors, and then planar transistors in 1959, which gave birth the concept of integrated circuit. But you see, straight out, there was no development of MOSFET during this time, and MOSFET only came around 1950. But at the moment, if you look at the integration of the devices, the first integration ultimately survived was the MOSFET because of its inherent properties, and that's why people are so much keen. And other side of the discovery, if you see, if you look at the PN junctions, then many sorts of devices have come out, including particularly the microwave and the solar cell and the optoelectronic as a whole, that is LEDs, lasers, photodiodes, photodetectors, and so many other devices. So this is, in a nutshell, the overall history of the semiconductor devices that we actually progress successively, and particularly people are looking for some alternative about this MOSFET switch to go for further or beyond. Now I will discuss about this MOSFET basics, that we know that MOSFET in general is a three-terminal device. However, it can also be work as a four-terminal device when the substrate is also being termed, or substrate is also being used as a terminal which is always generally grounded. But this particularly, if you can have a contact at the substrate, it can be used to engineer several properties of a MOSFET, including its threshold voltage. So MOSFET in general is a three-terminal device with a source, with a gate, and a drain. And if you look, this particular white region of this diagram, it is basically a semiconductor silicon crystal. And the red colors that I am trying to show here, it is basically a junction which is being formed between this source and the substrate, or the drain and the substrate. And particularly, in general, MOSFET, most of the cases we use because of its speed in inversion mode. So therefore, if we want to create an N-channel MOSFET, then we have to start from a P substrate, and we have to dope the source and drain region with N plus, means if the substrate got a doping concentration of 10 to the power 16 or 10 to the power 17 per centimeter cube, then the source and drain must be doped with 10 to the power 19 to 10 to the power 20 per centimeter cube. And therefore, if you have this N plus source and drain and P is the substrate, then you will get a PN junction. This is very important to control the property of a MOSFET, because electrically this PN region will create a depletion layer, and this depletion layer will actually electrically isolate the source from the substrate and the drain from the substrate. So that is the source drain, and the distance between the source drain is called the channel. And in terms of material, in the gate top, we got a polysilicon gate. Underneath that, there is a silicon dioxide material, which is an insulator. And underneath the silicon dioxide, there is a silicon semiconductor. So therefore, it is the metal oxide semiconductor. And the vertical direction, that is from polysilicon towards the substrate, if you apply a voltage in the vertical direction, then it will create a vertical electric field. And this vertical electric field will basically invite the minority carriers from the substrate towards this interfacial region. And therefore, in short time, this interfacial region, that is just below the silicon dioxide region, this entire region will be full of minority carriers, as we started this example with a p-type substrate. So therefore, it is the n-type carriers that will populate this region, which is the so-called channel. And the distance between the source and drain is a length, is called the channel length, which has immense importance to control the property. And my lecture will basically focus on this length, how it has been driven towards the quantum scale. So I'm not going to detail of this MOSFET operation because we know you know all these things. I'm just doing few minutes to recapitulate it, and I'm turning towards its physics. So the point is that whenever you will apply a vertical electric field, then a channel will be formed, and then if you apply a voltage between the source and drain, then it will create a lateral electric field. Under the application of these two orthogonal electric fields simultaneously, the MOSFET will be operational. So MOSFET, in general, a three-terminal device, and it will have to have at least two orthogonal electric fields working together. The vertical electric field is responsible to create a channel, and the lateral electric field will use the channel to drag the carrier or to drift the carriers from source to the drain region. That is the MOSFET. And if you look at the top right corner, it is the CMOS at the wafer level. So now if you look at that, then think about this left top corner picture, schematic of the MOSFET. And if we consider that it is on a p-type substrate, then the source and drain are n plus. So therefore, the corresponding band diagram from source to drain, you can see here, because the top region is P, so the left side will form a PN junction, whereas the right side will form another PN junction. And this is the band diagram at equilibrium. That means when there is no voltage applied at the gate and the drain. And similarly, if the MOSFET is on p-type substrate, then the corresponding band diagram will look like, which is at the middle of the right corner. But at any situation, if you start to apply gate voltages, then more the gate voltage is applied, the band will gradually go downwards. That means the barrier height between the source and channel, can you see the marker? I am moving it just to know whether you can see it. Can you see the marker I am moving?
Yes, sir.
Okay, fine. So this is the junction from the source to the channel. It is a PN junction, so there is a barrier for the electrons. And if it is this right one, I am moving the marker, so it is another PN junction, but it is hole is the carrier, so hole barrier increases downward. So in any situation, under normal condition, this barrier height restricts the carriers to flow from source to drain. So now, if you apply a gate voltage perpendicular to this one, then this barrier will gradually be lower and lower, and it will reach at certain voltage in a situation where the kinetic energy of the electrons in the source region will have sufficient energy to circumvent that lower barrier, and then it will reach to the channel. But now, if you start to apply a voltage between the source and drain, consider that the source is grounded and the drain you are applying a reverse bias. So the reverse band bending will be like that, which I am trying to show you in the with this marker at the left bottom corner of this slide. And you can see that once you can help the carriers to jump from the source to the channel, then the channel to drain regions, as it will have a reverse bias, then it will create a very high electric field. And because of this high electric field, the electron will start to drift through this channel to reach to the drain. So that is the basic operation in terms of band diagram. And if you look at the 3D band diagram, then you just please look at the top picture on the left side. What I'm trying to show here, it is a three-dimensional picture of the MOSFET, because MOSFET, it is 90-degree rotated. That means your vertical structures is now horizontal to give you the better idea. So therefore it is nothing but a MOS structure. And if you look at this front rectangular part, it is the source region or source terminal. And obviously on the other side, it is yellowish color, that is the drain terminal. So that is your MOSFET in a nutshell. So now if you apply a gate voltage, because of the gate voltage, there will be a band bending to create the inversion layer. And now, if you think about this entire MOSFET vertically of different slices, what I want to mean, please think about the MOSFET structure that I have shown at the beginning, and then think about the region below the oxide as different slices. So if you start from the top to go towards the bottom, you will get different slices of few angstrom thickness. Now if you apply a gate voltage, then the gate voltage, the maximum drop will be across the oxide layer. The remaining portion will be dropped within the semiconductor layer, which is the surface potential of the semiconductor. And if you go deeper and deeper within the semiconductor, then the voltage drop will also be gradually smaller and smaller. And finally, when the bulk of the semiconductor will start, the voltage drop will be zero. So I want to say or want to convey a message to you that when you will apply only a gate bias from the top, then each slices from the vertical direction towards the bottom, all these are the equipotential surface from source to drain. Could you please understand this part, or I should repeat it? Anyone, please?
Yes, sir. Yeah, we got
It's
it.
okay. Yeah. So
Yeah,
the point is
thank
that if you go from the tops towards the bottom, you will face some equipotential surface because you did not apply any voltage between the source and drain. Now, if you apply a voltage difference between the source and drain in such a way that the source is grounded, then there is a further band bending starting from the source to drain, and therefore there will be a further bending of these black horizontal lines, because these black horizontal lines in this 3D diagram is basically the side of the oxide layer. And therefore, if you apply the drain bias, these lines will not anymore be horizontal, rather there will be a bending perpendicular to the screen inside the laptop. And if I rotate it 90 degrees, then what I will see, that is this pink color graph underneath that where I am moving the marker. And that is the band bending from the source to drain. So the point is that whenever we are applying this potential difference and there is a band bending between the source and drain, then there is a variation of potential from the source and drain with respect to the distance. So therefore, dVdx, that is the electric field that will be created from source to drain. And because of this electric field, the electron will start to flow. Now, if you don't apply any source drain voltage, then there is no further band bending like this. And under this situation, when there is no voltage difference between the source and drain, think about the region underneath the oxide. There is an inversion layer, and that is therefore it is full of inversion charges, but the inversion charge distribution underneath this oxide layer is completely uniform. That means if I consider that no source drain voltage has been applied, only a voltage has been applied from the top, then the channel will form underneath this oxide layer, which is completely in a rectangular shape, uniform one. But the moment you will provide a reverse bias at the drain, then this reverse bias will start to balance or neutralize the inversion charges which has been created by the applied gate bias. And also, as the source is grounded and the drain you are applying a reverse bias, so therefore the maximum impact of the drain bias will be at the channel drain junction, and gradually if you move towards the source, this voltage difference will be gradually smaller and smaller, and finally at the source channel junction there is no such voltage drop. So if you now convert this concept to the balancing of the inversion charge, then the maximum inversion charge loss will happen at the channel drain junction. So therefore, when there was no source drain bias, the inversion layer was a perfect rectangle. But now as you started to apply the drain bias, reverse bias, therefore the amount of inversion charge at the drain end, means drain to channel junction region, will be much less than that at the source channel junction. That means the rectangular shape of the channel will start to convert to a trapezoid one, where the tapering will happen of the edge from source to the drain, which in terms gradually the amount of inversion charge will be lesser and lesser if you continue to increase the drain bias gradually. And at a certain drain bias with a given gate bias, a situation where will appear where actually the tip of this trapezoid will be very short, means there will be no inversion charge at the channel drain junction, and that is the beginning of pinch up. Now if you further increase the drain bias, then the pinch up point will gradually move towards the source, and therefore a depletion layer will be created between the edge of the electrical channel and the channel drain junction. And that is the depletion layer. If you continue to increase the drain bias, it will continue. In quantum manner, we can say that if you apply a certain amount of voltage Vg at the drain, then Vox will be dropped across the oxide layer. So the remaining Vg minus Vox, that will be dropped along the or across the channel. So if you take a certain point in the channel, you will have an effective voltage that is Vg minus Vox. Now if you apply a voltage Vd at the drain, then at that point of the channel, maybe not exactly Vd, but some less than Vd amount of voltage will also be additive with this Vg minus Vox, and these two are in opposite polarity. So the effective voltage at that point in the channel will be Vg minus Vox, minus VDS. Now, when VG minus Vox, that is the so-called gate voltage in the channel, will be much higher than the source drain bias VDS, the channel is very smooth and uniform. But the moment when VG minus Vox will be equal to VDS, then it is exactly the pinch off point. Now, when VG minus Vox will be higher than VDS, then the pinch off point will start to move towards the source, and as a result, a depletion layer will be formed between the pinch off tip to the source channel junction. And the standard current graph, we know that there are two types of graphs. One is the transfer characteristics and another is the output characteristics. I'm not going to detail into this part. You know all these things. So the point is that MOSFET performance parameters. At least there are 12 parameters of a MOSFET to keep you everything in up to date. The first one is the threshold voltage. So we have understood that there is a barrier height between the source and the channel, so you need to reduce the barrier height so that the carrier can be injected from the source to the channel. So now threshold voltage, it is the minimum channel where the barrier height will come down to a value where the carriers from the source will be able to circumvent that barrier and then can travel through the channel to reach to that drain. And if you say, how can you extrapolate this value? How can you extract it value? So if you consult the expression for current, then you can see that if you make the current by any means zero, then where this current extrapolation graph will meet the voltage channel, that will be the value of the threshold voltage. So therefore, if you look at this graph, and if you think about these transfer characteristics, the particular linear region, and if you draw a line following that linear region, when this line will touch the voltage axis, that is actually the value for threshold voltage. So this is the threshold voltage, which is an extremely important parameter, because in course of time we will see that this threshold voltage will control exactly the power dissipation of a device. If the threshold voltage is lesser and lesser, definitely the device will be better. However, at certain point, if the threshold voltage is too low, then there will be an automatic transport of carriers from the source to the channel, and therefore you will get a sustained leakage current, which is deleterious for or in terms of the static power dissipation of the device. So threshold voltage, how can you engineer it? There are three options to control the threshold voltage. One is the doping concentration. Second is the oxide thickness. Higher the doping concentration, higher will be the threshold voltage. And higher is the oxide thickness, higher will be the threshold voltage. And also you need to keep in mind about the difference of Fermi levels between the metal, that is the gate material, and the channel material. And also, if you reduce the doping concentration at your desire to reduce the threshold voltage, plus please keep in mind that if the doping concentration is too small, then also the current value will be lower. So therefore it needs an optimization about what is your current specification of the device at the output level, and then what should be the doping concentration that you have to fix up. Second, thinner the oxide, lower will be the threshold voltage. But if you reduce the thickness in a drastic manner, there will be several types of tunneling currents that will come into play. That is further northern tunneling, direct tunneling, and Pule-Frankel tunneling. So that also needs an optimization. Second, MOSFETs can be applied particularly in two ways. If you only think about its off state, if I request you to consult the graph at the left top corner, and then particularly the region I am moving by marker. This is the off state of the MOSFET. And if you look on the other side, the on state of the current, and there is a transition between the off to the on state. Here I am showing few parameters together. If you look at one graph I am showing at the top of others, although there or its higher drive current is not so high. So as a result, if you think that MOSFET is just a switch, then it has two states. One is the off state, which is below the threshold voltage, and another is the on state, which is far above the threshold voltage. And the region in between these two, it is the transition region. And therefore, true it is for the output characteristics. And other parameter which is also very important, it is the transconductance, which is basically is the measure of the rate of change of drain current with respect to the gate voltage. So therefore, if you look, this is the typical MOSFET transfer characteristics, and if you take its first derivative, then it can easily shows that at certain point it will have a peak and then it will further fall. Now the point is that this peak value is called the maximum value of the transconductance. It is higher the better. And second or third point, it is the output characteristics. And if you take the rate of change of output characteristics with respect to the output voltage, that is del ID, del VD, then it will give you the output conductance of a MOSFET. And then the most important point that I like to highlight here, it is the subthreshold swing. And subthreshold swing of a MOSFET, if you see what I am trying to plot at the top of the right corner of this slide, is that it is a logarithmic graph of the current with respect to the gate voltage. And if you say, I marked one region, and which is basically a change of current of one decade. That is, if you take the higher current value at say 10 to the power minus 6, an example, and the lower value of 10 to the power minus 5. So there is a change of one order of current. Or if you take the maximum current to be 10 to the power minus 6 and minimum current to be 10 to the power minus 5, it is again one decade. 5e 10 to the power 7 to 5e 10 to the power 6. Again, it is one decade. So what I want to say that think or take the transfer characteristics of a MOSFET, and then you like to see the one decade change of current. And to do this one decade change of current, you look at how much change of the voltage. And this is basically the slope. But if you take the inverse of the slope, that is called the subthreshold swing of this MOSFET. And subthreshold swing is actually the measure of the speed of a MOSFET. Because in entire MOSFET or CMOS technology, people always look for two things. One is the low power dissipation, and second is how fast the system can work. And this is the key parameter of this conventional MOSFET that is called subthreshold swing, which is basically the inverse of the slope of the IV characteristics for a change of current of one decade. So in terms of mathematical expression, you can say that subthreshold swing, SS, it is basically log of D log of ID dVGS inverse. And if you simplify it, finally it will turn out to be log 10 KT by Q 1 plus CD by Cox. Very interesting thing now you can say that log 10 is a constant, and for a given temperature, Kt by Q is also a constant because K is the Boltzmann constant, T is the temperature at which the device works, and Q is the electronic charge. So subthreshold swing should be smallest for the better operation of a MOSFET or faster operation of a MOSFET. But if you see here, the subthreshold swing will be minimum only if here CD is 0. Because everything is constant outside the bracket. So only parameter that can you control is CD because it is 1 plus something. So if CD is 0, that will give you the minimum value. And for any semiconductor device, it is quite impossible to have no depletion. So therefore, ideal value when CD is 0, and if you put these values, log 10 it is 2.3 something, and kT by Q it is 26 millielectron volt. So if you simplify it, it will give you 10 millivolt. So 10 millivolt per decade, this is the, sorry, it was a mistake. It is the 60 millivolt because it is 26 millielectron volt multiplied by log 10, which is 2.3. So if you multiply that, it will give you almost 60 millielectron volt value. So the subthreshold swing, which is 60 millivolt per decade, it is the minimum achievable subthreshold swing value for a classical MOSFET. So how much design you do, how much robust technology you devise for fabrication, there is no option to go below 60 millivolt per decade speed of a conventional MOSFET. And that puts the bottleneck of the classical MOSFET. And therefore, if you look at the equivalent circuit, MOSFET is nothing but a combination of few resistors and few capacitors. And the capacitors are of maybe three types. One is the oxide capacitor. Another is the capacitor between the oxide layer and the depletion layer that will be formed with the channel or below the channel. And then there is another capacitor between the substrate point towards the gate layer. And also there may be a capacitance between the source and drain region because there is also a PN junction. So altogether, MOSFETs is basically an assimilation or amalgamation of few capacitors and resistors, which is the equivalent circuit of a MOSFET. So whenever a MOSFET device will be placed in a circuit, the circuit will see he or it does not understand or does not know what is a MOSFET or anything. It will face some resistance and capacitance altogether, and that is the equivalent circuit from where you can measure the mobility. And mobility, just we have discussed, you see, transconductance or output conductance, GD, we have discussed. So it's a function of output conductance, which can be measured from the current voltage output characteristics. Then L effective, that is the effective electrical length of the channel, that is the distance from the source channel junction to the tip of that particular channel point that we have discussed. And Qn is the inversion charge, and W is the width of the device. So everything is known. You can measure L effective, you can measure output conductance, you know what is your W because it is the design specification of the device, but you don't know Qn. Qn, it is the amount of channel charge that will be generated when only the gate voltage applied. So how can you measure the channel charge or inversion charge? And the technique which is followed to do that is the split CV technique measurement. So split CV technique measurement, if you see the circuits on top, there are two connections. In one connection, the gate is floating, the gate and the substrate is connected and the source and drain are floating. So this is one capacitance. If you measure the capacitance here, you will get a curve that is CV, capacitance voltage curve. And in other measurement, your gate is floating, but you are measuring the capacitance between the substrate with the source and drain here with the substrate. When the source and drain are sorted and capacitance are measured, then these two capacitors are coming in parallel. So this is the split CV technique. Easily you can measure it. Then you will get two capacitors, which is shown in the right bottom of this slide, CGC and CGB. One is the channel capacitor and another is the gate to substrate capacitor. Now, if you integrate the CGC with respect to voltage or the area under the curve of CGC versus VG, it will give you some charge because C into V, and that charge is the inversion charge. So that's the way you can calculate or estimate the mobility of a MOSFET device. Now, how to go beyond the process or how you can improve the performance of such a device. To do that, I will request you all to focus on these two expressions. One is the current expression in the linear region, and another is the current expression in the saturation region, where everything is known. Epsilon ox is the oxide dielectric constant, then epsilon 0 is the permittivity, mu is the mobility, T ox is the oxide thickness, W by L, it is the aspect ratio of the MOSFET, that is width by channel length, Vg is the applied gas voltage externally, Vd is the applied drain voltage externally, and Vth is the threshold voltage of the MOSFET. And in the saturation region, it will be saturated, as I mentioned you, when Vg minus Vth will be equal to Vd. So finally at the saturation region, the expression will be turned to finally Vg minus Vth whole square by 2. Now, how can you improve the performance of the device? It is the comparative table. If the threshold voltage is lower, it is a good MOSFET. If the offset leakage current is lower, it is a good MOSFET. For a good MOSFET, the on current should be higher. For a good MOSFET, the transconductance should be higher. The good MOSFET will give you the output conductance or channel conductance to also be higher. The subthreshold swing should be smaller. Drain voltage should be lower so that the power dissipation will be less, and channel mobility should be as higher as possible. Source drain resistance should be lower as possible, and drain induced barrier lowering I will introduce later, that should be lower and lower. So this is the parameter matrix. Only 12 to 11 to 12 parameters are sufficient to understand about the performance of a MOSFET, and this is the guiding route that how or what to do for designing a good MOSFET. So this is the current expression you can see at the top. Threshold voltage you can say. Transconductance, as we have derived in the previous slide, it was del ID by del Vg. So you can see that. What I want to request you, one thing. These current expressions, I or Gm or Gd, you can think these parameters to be constituted of two different types of set of parameters. One is geometry related and another is the material related. Either you look for the current, or you look for the transconductance, or you look for the output conductance. The geometric parameters is the width of the device and the L, length, channel length of the device. Tox is the oxide thickness. Everything is the geometric parameter. Other parameters are set of parameters are completely material dependent, that is mobility, insulator dielectric constant, and permittivity of the free space. And it is also true for output conductance. Now we learned from the previous slide that more the current is the better, means drive current. More the GM is better, more the GD is better, that will give you a better device. And how can you improve it? Either you can increase W, that is the width of the device, but mind that you cannot increase the width of the device, because if you increase the width of the device, then the area of the gate will be higher and higher. So therefore the packing density will be lower and lower. That means you cannot increase the stacking density, and as a result, you cannot implement more functionalities in a chip. Because to implement functionalities, you need gates, NAND gates, and other gates, and those NAND gates require transistors. If the transistors are of bigger area, then the lesser number of transistors can be integrated within a given area. So increase of W is totally prohibited. So now you are having two options available. One is the TOX to reduce gradually, that is the oxide thickness, and other is the channel length that can be reduced gradually, and that will improve your performance. So the issue is, on the other side, mobility you can increase, or the dielectric constant you can increase. But in terms of profit, the industries are very much reluctant to change their technology. And for them, changing or incorporating a new material into a technology route is very much challenging than to reduce the geometry. So therefore, from 1970 onwards, Intel particularly took the leadership. Definitely IBM was there, but Intel took the entire leadership and gradually started to reduce the device oxide thickness and channel length. And this particular approach is called the scaling down of device dimensions. So therefore, technically we can say that scaling down of device dimensions has been the preferred route from 1970 onwards. So therefore, possible solutions of reduction, as we mentioned in the previous discussion, that decrease the transistor body factor. I will come later, just wait. So the issue is what people did from 1970 onwards. Just I am requesting you to go through the arrow, because it's a huge number of different MOSFETs that has been introduced in different years, starting from 1960 by Bell Labs, and then IC technology, integrated circuit 1961, and then the Fairchild fast CMOS in 1963, and in 1964 the commercial CMOS IC, 1965 the DRAM first introduced, and 1968 the polysilicon as the gate material was included in the MOS technology, and then 1960 first one FET DRAM was introduced, then UV, EPROM, and 71 microprocessor, then 74 digital watch, scaling transistor, that is Dennard law, constant voltage scaling and constant field scaling, 1974. 78, it was the use of implantation technology to make the junction sharper, and then floating gate. After that, CMOS, ion implanted CMOS in 1980. The technology plasma etching was introduced, and within this time in 94, the MOSFET has been scaled down to 0.525 micrometer, that is 250 nanometer scale. And 1986, the 100 nanometer MOSFET, silicon MOSFET was introduced. And then the concept in 1993, double gate MOSFET, and 2003, it was the strained silicon MOSFET. And then in 2007, the hafnium oxide was introduced instead of silicon dioxide. After that, gate all around, then 32 nanometer gate length. Is there any problem? Is there any problem?
No, sir, no.
Okay,
Sir,
some
some,
words have come.
yeah.
Oh, so in 2011, it was the 22 nanometer multi-gate FET, and then 2001, that is just 10 years, 12 years ago, 22 nanometer gate has been introduced. So what is important to check that now in the bottom table, the gate length of the MOSFET is gradually scaling down in 2024. Just last year, it was supposed to be of 7 nanometer in length. So that is the entire chronological change of the MOSFET gate length sustainedly, because it was the prep for root to reduce the geometry gradually. And of course, physics will never die. So what happens when the people started to create this drastic scaling down from few micrometer to quantum length 7.5 nanometer, then physics started to play the role. And if you think as well, the different types of physics had to explore for the technologists to tackle the physics related problem. And if you look back, it was 1955 where silicon and germanium conduction band and deformation potential field, high field, was introduced, the concept. Then BTE in semiconductors, that is impurities and phonon scattering, was introduced. And then in 1964, band structure calculation, that is Monte Carlo simulations for semiconductors, that was introduced. In 1965, linear parabolic oxidation model, that is Dilgrove model, that is a very famous model because still people are using this model during this oxidation, silicon dioxide growth. And then 1966, the first two-dimensional electron gas was introduced, that is so-called quantum effect. And then 1967, capacitance technique by Nikolian Gertzberg was discovered. And in 1974, drip diffusion emission model device simulator was developed. 1975, the discovery of quantum Hall effect gave a new direction. And then it was observed in 1979. 1981, identification of native interface states, which was very essential to control. And then full band Monte Carlo simulation was developed in 1981, and it was delivered to the market. And then it is the fractional quantum. Basically, quantum confinement was observed first in 1982, and then 1988 full band simulation again. And then the latest model that is now people are converging is the NEGF, which was first introduced to tackle the transport of MOSFET technologies or MOSFET devices, that is in 1992. And what is the fate of the oxide? In 1975, a MOSFET was using 20 micrometer thick oxide, 250 nanometer thick oxide, and 20 micron was the gate length of the MOSFET. In 1980, it turned down to 10 micrometer gate length and 150 nanometer oxide thickness. In 1985, the gate length turned to 5 micrometer and TOX came to 70 nanometer. In 1990, gate length was 1 micrometer, TOX was 50 nanometer. When the gate length is 350 nanometer, the oxide thickness was 8 nanometer. When it was in 2000, it was 180 nanometer MOSFET node, where the oxide thickness came down to 3 nanometer. And in 2005, 65 nanometer gate length MOSFET was introduced, where oxide thickness is taken to be 1.4 nanometer, and so on. Now, in 20, it was the 11 nanometer gate length and MOSFET oxide thickness. Nobody was clear about that, which I will introduce in course of time, because nowadays the MOSFET oxide thickness has been of sub-nanometer, means 0.7, 0.5 nanometer, which is basically 5 to 7 angstrom, which is unbelievable because at least you need 2 oxygen and 1 silicon to make a silicon dioxide molecule. I am coming to highlight in course of time. So challenges, it is the instability of the silicon dioxide as the gate insulator, lots of defect states, traps, interface states, several trapping effects or mechanism, hot electron effects, threshold voltage shape, oxide background. So all these are the undesired thing, which finally led to very much high unexpected level of leakage current. So focus to reduce the leakage current, go for the alternate gate insulator. To increase the mobility, because scaling down, physics is basically putting the challenge and telling that no, you cannot go beyond this. So therefore, we need to find out the alternative materials with high mobility, and also whether we can go a paradigm shift from the MOSFET as a switch to some alternative switches, which is the action area now. I'm not going to read it because this is the equations to tackling the MOSFET transport in course of time. You can see easily that different technological node and MOSFET gate length had to use different transport equations. So challenges to sustain performance improvement by gradual scaling. The challenge is the more functionality, higher packing density, higher speed, lesser power. All these are contradictory requirements. If we want to increase functionality in single chip, many functionalities if we want to incorporate, then definitely you need more transistors. So if you want to put the higher number of transistors in a given area, so you need higher packing density. More transistors will work, the circuit length will be higher, but its speed must have to be higher, which is completely opposite requirement. And higher transistors will run, less power consumption will be there. So it's a very interesting domain. Three, balancing contradictory requirement actually gave the shape of the entire CMOS technology evolution. So if you see, this is the chronological development or scaling down of the MOSFET gate length, and now we are very much within the narrow era. That means the entire MOSFET dimension and scale has been transformed from micrometer to nanometer. So what are the challenges? There are five basic challenges that put a really hard bottleneck for the progress from one technology node to another one. The drain-induced barrier lowering, DIBL, and punch-through. Then surface scattering, the velocity saturation, impact ionization, and hot electrons. All these things are very detrimental. So the point is that what is drain-induced barrier lowering? If you remember one of my slides where I put the drain reverse bias and trying to highlight that after certain drain bias, the pit point of the pinch off will gradually move towards the source, and therefore a depletion region will be created between the junction of channel drain to the end of the electrical channel. Now, as technology progressed, we understood that the distance between the source and drain were gradually and forcibly reduced. So as a result, the drain voltage extended its effect or depletion region up to the drain. So what happened during this process of scaling, as the effect of drain voltage affected the source channel barrier, so not only the gate voltage will reduce the barrier, at extremely scaled down MOSFET, the drain will be so nearer to the source that the drain bias will also force the barrier at the source channel junction. So therefore it is called DIBL, drain induced barrier lowering at the source. And because of this, if we don't have the knowledge about this one or quantification about this one, then you will have an extra barrier lowering. That means the threshold voltage will be lower. So if you design as an integrated circuit VLSI chip without incorporating the effect of this DIBL, then after fabrication you will see that your MOSFET will exhibit lesser threshold voltage than you design, and consequently it will provide more leakage current, which in turn will create more static power dissipation. So that's why below 0.5 micrometer scale means after or below 500 nanometer gate length, the DIBL was very crucial to control. And second, as it is scaled down, so therefore it may happen that the depletion layer will touch the source channel junction from the drain. In general, in conventional MOSFET, the only one requirement was that the vertical electric field must have to be higher than the lateral electric field to maintain the electrostatic integrity of the entire MOSFET device. But as you continue to scale down, the channel length has been aggressively scaled down with respect to the oxide thickness. So as a result, if you reduce the oxide thickness, that will also increase the vertical electric field. But since the lateral direction has been aggressively scaled down with respect to the vertical direction, so therefore the vertical electric field increase, but not at that level of the lateral electric field. So therefore, in course of time during this scaling, the lateral electric field has been increased with a rapid pace with respect to the vertical electric field. And that's why punch through may happen. And if the channel is punched through, then there is no channel. So the current through the channel will be completely controlled by generation recombination process of the minority carriers. So we have to be very careful about it. Otherwise, you will never get the proper specification of the integrated circuit after design and fabrication. Surface scattering, because of the high vertical electric field, the carriers will try to move near to the interface and which will face surface scattering, which will reduce the current drastically. Velocity saturation. Another important point of the conventional MOSFET is that first pinch up and then saturation. Because in a conventional MOSFET, saturation will never happen if the pinch up does not happen. But in the ultra scale down MOSFET, you will not get any opportunity to do pinch off. Before that, as the distance between the source and drain is too small, so therefore the electric field is too high laterally, so the electron will reach its saturation velocity immediately. So therefore, you will lose the control of the MOSFET, because once you apply the electric field critical, more than the critical electric field, the current will reach to the saturation. Then how can you control it? It is always in saturation. So there is no option to engineer it. So therefore, velocity saturation is one detrimental nature of a scaled down MOSFET. Impact ionization. Since the carriers are moving through the crystal of the silicon, and it has a very high electric field, so it has a very high kinetic energy. So those high kinetic energy electron will hit the lattice atoms, and it will knock down some secondary electrons from those lattice atoms, and those secondary electrons will also be under strong electrical field. So immediately, like a chain reaction, the drain current will increase. So as a result, instead of achieving a saturation, the current in the up just beginning at the saturation will increase exponentially because of this impact ionization. You will never get the saturation. So there is no concept of such MOSFETs to be used in the digital electronics. Second is and last is the hot electrons. Hot electrons are basically the electrons which will have higher energy than the lattice. So when the electrons are moving with high velocity, with high kinetic energy, then because of that high kinetic energy, its temperature will be very high. And because of this high kinetic energy, the electrons, when they will move towards the drain, it will have more kinetic energy. So therefore, it will continue to heat the oxide layer. And during aging, these oxide layers will be gradually knocked down and will be broken electrically and also by molecular level. And therefore, in a very short time, you will lose the reliability of the device because of this leakage current. Gate will fail. So the consequence as a result is an unexpected level of leakage currents, and particularly there are 6 types of leakage currents that will jeopardize the performance of a normal MOSFET. One is the gate leakage. due to the degradation of the oxide and because of the thinning of the oxide, there are few tunneling mechanisms that will come into play. That is the further Nordheim tunneling, FN tunneling, PF tunneling, and then subsequently followed by the direct tunneling. Then subthreshold leakage current, when the distance between the source and drain will be less, so there will be a carrier concentration gradient from the source to drain. And since the distance is too small, so therefore the gradient will also be too steep, so the diffusion force will increase. And as a result, prior to the threshold of the MOSFET, before the formation of the channel, people will start to get some current from the source to drain because of the diffusion mechanism. And that's why this diffusion mechanism will be too high. Leakage current due to DIBL, because as we mentioned already, when the drain barrier will be unexpectedly reduced by the drain bias, then extra leakage current will come, which will contribute to the static power dissipation. Then junction leakage. As you see the arrow I am showing here between the N plus region drain to the substrate, this is a PN junction. So when the MOSFET is in operation, this PN junction is reverse biased. So you will get always a reverse saturation current. And that is not good, because if the MOSFET current, if it is gradually reduced, then the microampere range, mind that this reverse saturation current in a PN silicon PN junction is of the order of 0.1 microampere to 1 microampere. And then gate induced barrier lowering, mind that, look about this one, I am focusing the arrow. Here I try to show that the some portion of the drain and source has gone beneath the gate layer, which is called the gate and drain overlap. So whenever you will apply a voltage difference between the gate and the drain, then an enormous electric field will be created in this region of the material. And as a result, the conduction and valence band of semiconductor will become in closer, steeper region. And because of this, there will be a high possibility of current transition, that is called band-to-band tunneling. And because of this, the band-to-band tunneling current will come, which is also unexpected, because you are focusing for the channel current only, but this undesired component of current will appear. And therefore, as this barrier lowering is happening by the gate bias in the drain region, so that's why it is called GIDL, or gate induced drain leakage current. And leakage current due to hot carriers, that I have already discussed. So I am not going to read this one because it is more related to technology. Now I will want to share one important graph that has actually gave a very troublesome situation during around 2006. What is this graph? Those who are working in the design of VLSI chip, it is very important to them. If you think about this, I tried to show one thing, that is the normalized power dissipation. Power dissipation in a MOSFET device can be of two types. One is the static power dissipation, and another was the dynamic power dissipation. So in static power dissipation, which is that when the MOSFET is generally in off condition, then the power dissipation will be termed as the static power dissipation. And when the device is working or the circuit is on, then the power dissipation is called the static power dissipation. So it is quite obvious that when the system is operational, then the static power dissipation will be more. The dynamic power dissipation will be more than the static power dissipation. But you see what has happened. As the year progressed, even last 4-5 years, I am showing the data, the gate length has been gradually scaled down, and as a result, the oxide thickness has also been scaled down. So what actually gave the result that the static power dissipation or the subthreshold threshold leakage current dissipation and the gate leakage dissipation, they started to increase rapidly. So at the beginning of 90s and up to 2050, the dynamic power dissipation of the device has not been increased too much. whereas the static power dissipation has been increased too high. And around 2006, a situation actually appeared where the static power dissipation took over the dynamic power dissipation. That means if you keep your circuit on, you will have less power dissipation than you keep your circuit off. And that gave a real trouble because it is nothing but the battery drainage of the laptop or mobile phone. So what happened then? People understood that since the oxide has also been scaled down in a very rapid pace, so therefore the oxide thickness has been, silicon dioxide thickness has been of the order of 1 or 1.5 nanometer. And at this situation, the direct tunneling was enormous. And because of that, people got huge leakage current through this oxide layer. So what they thought during that time, that they did not want to lose the electrostatic integrity of the device. So therefore, they wanted to keep the capacitance constant. So now, say for example, the silicon dioxide has the oxide thickness Tox, and the silicon dioxide has the dielectric constant epsilon ox. And think about another dielectric material whose dielectric constant is, say, epsilon hk, and its thickness is thk, high k. Hk, I am using that suffix. So now if you take the ratio, you choose the ratio in such a way that epsilon ox by Tox, it is the oxide capacitance per unit area. So if epsilon ox by Tox equals to the epsilon high k divided by T high k. So now if you replace T high k, it will be epsilon high k divided by epsilon ox into epsilon into Tox, which means we are people tried to find out some equivalent oxide thickness of high K dielectric material, and which is nothing but the multiplier of the ratio between the high K dielectric material and the silicon dioxide material. Silicon dioxide has a dielectric constant of 3.9, whereas high K dielectric materials like TiO2, like hafnium oxide, like zirconium oxide, like alumina, like silicon nitride, all these materials have higher dielectric constant than silicon. So a huge research took place during 1995 to 2005, around 10 years. During that time, people tried to find out many options of the high K dielectric materials, and they were looking for the best one so that it will have a good electrical interface quality with silicon. And eventually, hafnium oxide has termed or emerged to be the best one. I'm not going to detail because of the time constraint. So that's why from 2005 onwards, people tried or people incorporated hafnium dioxide as the gate oxide instead of silicon dioxide. And immensely when they put what they got, hafnium oxide got a dielectric constant of 24, and silicon dioxide has a dielectric constant of 3.9. So if you take the ratio between these two dielectric constants, it will be around 6. So THK, that is thickness of the high K dielectric material, will be 6 times higher than TOX, that is oxide silicon dioxide thickness. So as a result, you will get the similar electrical integrity if you replace 1 angstrom of silicon dioxide by 6 angstrom of hafnium oxide, and people did it. And as the hafnium oxide thickness increased, so therefore it reduces the direct leakage current, and therefore the static power dissipation started to decrease. So if you look at this pink graph, that is the trajectory by which the power dissipation has been reduced. And still we are using this technology. So root cause of short channel effect. Root cause of short channel effect is that the vertical electric field loses the control over the lateral electric field. So therefore, if you reduce the gate length, the lateral electric field, if the gate length is L and if the voltage is applied VD between the source and drain, then the lateral electric field value is VD by L. On the other side, if the oxide thickness is Tox and you are applying a voltage gate VG, then VG by Tox or Vox by Tox, that is the electric field in the vertical direction. Now, since the L, that is the gate length, has been scaled down with a very rapid pace, so the lateral electric field has also started to increase in a very rapid way. So therefore, the vertical electric field actually lost its control over the lateral electric field. So
Yes, sir.
therefore, sure,
Sir, sorry, we are not able to see your PPT, sir.
not yet. Okay.
Yes, sir.
So should I go back again?
No, just now only. Just 1 minute.
It is okay. It is okay, sir.
Now?
It is okay, sir. It is fine.
Okay. So the point is that when as you started to scale down the length in a rapid pace, so lateral electric field started to take over the control over the vertical electric field. So then people tried to realize that, okay, by any means, we have to increase the vertical electric field. So what are the options available? Then people tried to think about that we are using a single gate. So instead of a single gate, if we use a double gate, then definitely the vertical electric field will be double compared to the single one. And that is the beginning of the journey of a planar MOSFET to the three-dimensional MOSFET. Because if you have a gate and if you want to create two gates out of that, then if you think about that, your gate is elevated from the silicon surface and then you oxide both in left and right side, then it will create a, and then deposit the metal, then it will give you gate 1 and gate 2. One gate in the left hand side, another gate in the right hand side, and in between these two gates you will get the channel. And that gave the idea of double gate MOSFETs. Then after a few times people realized that, okay, if we can create the double gate MOSFET, then why we not create another gate on the top? And that gave the idea of triple gate MOSFET. So if you look at the left corner of the slide, you can see the architecture of the double gate MOSFET, so that the MOSFET can be, electric field can be double from the vertical direction with the channel. So there are three types of orientations possible, but at the end of the day, it is a three-dimensional MOSFET. And then if you go for the first, you take tri-gate. I am moving the marker. So it is the tri-gate. So instead of the double gate, you can create another gate on the top. So it is a three-terminal gate also. People also told it is the FinFET. Then people also realized that, okay, if we can create the three-gate FET, then why we should not go for the four-gate FET altogether? But you see the marker I am moving, gate-all-around structure, it is just because to increase the vertical electric field across the channel by increasing the number of gates. Then people realize that, okay, then what's wrong? We are now living or moving towards the nanotechnology, and it is now easier to grow nanowire than this type of structure of gate all around. And if you have a nanowire, and if you can wrap the nanowire to be a channel by a gate of cylindrical shape, then that will ensure maximum electric field in the axial region, because this is the maximum possibility of having vertical electric field. And that gave birth the idea of nanoscale FET, where it is definitely one type of gate all around MOSFET, but it is naturally the nanowire FET. So the point is very interesting. In one side, the nanotechnology has been emerged, and now we have the technology how to grow nanowires, nanotube, nanorod, and other nanostructures. And now also the MOSFET, the mainstream electronics, is also demanding for this type of geometry to maximize the vertical electric field to achieve the superior performance of MOSFET. And therefore, it is a merging together of nanotechnology and the evolution of the MOSFET to come down on the same platform. So that is one of the ways that how the classical MOSFET of 70 or 50 or 10 micrometer gate length has come down to the channel of 5 nanometer, 7 nanometer, and the diameter of 3 nanometer and 4 nanometer. Because if you come down to this level, then again physics will not die. So what will happen? Several quantum mechanical effects will come to play together, and therefore you cannot have the option to model these transport of such nanometer MOSFETs in terms of classical equations or drift diffusion model. You must have to incorporate the quantum mechanical effect and quantum modeling along with the incorporation of NEGF, because NEGF will take any types of local non-uniformities during the transport. Other side of this one to tackle is that as you can remember, I showed at the beginning that if you think about the current in a MOSFET can be of two types of control parameters. One was that the material where mobility played the important role. And therefore, another route people took during 2000, or better to say from 1990, and it took Intel to bring its product in 2003, which is called the strained silicon MOSFET. And what is the game behind it? If you look at the graph I am showing on the right hand side of this slide, correct, where I am showing you one thing, the strain versus or stress versus mobility. That means if you have a silicon and if you have the technology to strain the silicon epitaxial layer, then that strain, it is an energy, and that strain energy will modify the band structure of silicon. And as a result, what will happen? The mobility of electron and holes will automatically increase. So several people and group work together. So that's why several graphs are shown here. And here the points I'm showing, including our data, Intel data, IBM data, Toshiba data, there are all the data available. Those who did research on the strain silicon MOSFET and they checked the mobility enhancement factor, that has been 2 times or so. So therefore, strain incorporation has been a very eternal technology now to increase the mobility. So not only the geometry, or I should better say that we could reach to the end of the geometric scaling of the MOSFET. And now we are basically in the quantum dot era. If I get an opportunity in another lecture, we will highlight it. But that is the end of the roadshow of the scaling down approach. Alternative approaches were this. That is the strain incorporation. And the first commercial product with 65 nanometer technology was brought down by Intel in 2003. And the MOSFETs and the chips we are using nowadays from that onwards is totally controlled by strained silicon. It's a big area, but only just I am sharing with you few concepts that how it was approached. 2 approaches. Gautam, should I continue or stop?
No, sir. Continue, sir. Please.
Okay. So the point is that we have 2 options available. The first one called the so-called global straining technology, which was followed by IBM, and another was the right one I am showing, that is the strain engineering from the lateral direction, which was followed by Intel. So what is the concept of strain engineering? Is that silicon and germanium have their different lattice constants. Silicon got a lattice constant of 5.43 angstrom, whereas germanium has a lattice constant of 5.63 angstrom. So there is a 4.2% lattice mismatch between silicon and germanium. So if you have the technology to grow either silicon on germanium or germanium on silicon, then there is a lattice mismatch. And because of this lattice mismatch, there will be a strain incorporation. Because, say, for example, if you use germanium as the substrate with a lattice constant of 5.63 angstrom, and if you grow silicon epitaxial layer on top of that, then the silicon, as it is the epitaxial layer and it is growing on silicon, growing on germanium, so silicon atoms will be forced to compelled to accommodate the lattice constant of germanium. So since it will be forced to accommodate the lattice constant of germanium, so therefore silicon lattice itself will be expanded with respect to its original lattice constants, and by this way the silicon lattice will feel a strain, and since its lattice constant is increased, so therefore it will deliver the tensile strain in the grown epitaxial layer. On the other hand, if you grow germanium on top of silicon substrate, then the germanium lattice will be forced to accommodate the lattice constant of silicon, so therefore the germanium lattice will be squeezed, and that is the source of incorporation of compressive strain in the epitaxial layer. So in general, we can say that by growing the material having two different lattice constant in one top of other, you have the technology to create strained materials, and if you use this strained material as your channel, then obviously this strained material will have higher mobility, and therefore you will get superior performance MOSFET, which is the so-called strained silicon MOSFET. So this first technology was first invented by IBM and used, but Intel did a different thing. What they did actually, they took the normal conventional silicon CMOS technology, and in place of source drain, what they did, they deposited silicon germanium, which is having a different lattice constant than silicon. And silicon germanium is an alloy. So therefore, the silicon germanium lattice constant is higher than silicon. So when they deposited and annealed it, the silicon germanium started to push the channel region of silicon, which is the technique by which you can incorporate compressive strain. And they did this technology because of a different reason. Because when those who are working in the VLSI design, you know that hole mobility is lesser than silicon mobility, electron mobility. So therefore, in terms of design to compensate the current of in MOSFET, people had to increase the area of the width of the P MOSFET region. But this technique, compressive strain, actually is capable of increasing the mobility for the holes. So therefore, Intel tried to reduce, to increase the packing density, they tried to reduce the number, tried to reduce the area of a single MOSFET, and that's why they were frantically eager to increase the mobility of the hole. And this is the compressive strain which they got the idea, and they in all MOSFETs, P-channel MOSFETs, they incorporated this compressive strain instead of conventional silicon channel to increase the mobility of hole, and that gave them the very good result, and that we are using at the time. I'm not going to elaborate it because of time, because now it is already 9. So the point is that just to give an idea, this is the data or the devices fabricated by ourselves in England when I was in England. Just to give you the idea that you see, it is a comparison of strained silicon. The dotted line is the silicon mobility, and the red color is the university mobility card. And if you see the blue points on the top, that is the strained silicon mobility. So this is an idea that yes, strained silicon could increase the mobility of the silicon channel, and none of the MOSFETs at this time is a conventional silicon. It is the strained silicon. And also you can engineer the threshold voltage by controlling the amount of strain. But another side that we must have to highlight, else it will not be complete, because it is the nanoscale. When the nanoscale MOSFET we are dealing with, because nowadays the scale down has been so small, what is happening, MOSFET is a process. When the device is being fabricated, that entire process is going through different thermal cycles. Sometimes the temperature it is required is around 900 degree to 1000 degrees centigrade for oxidation or annealing of the dopants. But Since the MOSFET is an assimilation of different types of materials like silicon, silicon dioxide or hafnium oxide, metal, silicides, and so on. So therefore, when the device is under processing, all the material systems are passing through these different thermal cycles. But the different materials have their different thermal expansion and compression coefficient. So therefore, when they are getting heated, they will have different compression or expression, cooling down and heating up. And during this compression and expression, the materials will inherit some amount of interfacial strain. Since this strain will automatically come, that's why it is called the process induced strain. Means whenever you will go for processing the MOSFET device, the strain will automatically be incorporated. So now, if you are a design engineer, you must have to have the idea about all this process engineering and process induced strain. Otherwise, your design will never deliver the circuit or device up to your specification, because the strain will control the mobility, the strain will control the current, the strain will control the offset current, the strain will control the threshold voltage. I am not going to detail. So these are the things. In all these are collected from internet, so I am not going to read it. The different types of MOSFETs architectures that people tried in very recent times to go for that multi-gate and other types of FETs. So from the strain one, I will conclude a statement like this, that induced strain and scaling augment each other to sustain gradual performance enhancement. Because strain will increase, but if you strain, you can also scale. So these two are things. So now we are living in the era of nanowire FET. I am not going to detail. This picture, the second one on the left hand side, I have already shown you, but this is the picture of the MOSFET. Correct. And this is the MOSFETs we are dealing at the moment. Actually, we have crossed this limit also in terms of research, but people could not properly demonstrate it yet. But what is happening in this type of MOSFET? What can you do? What are the transport properties that you can control? Now, it is basically you must have to develop, if you want to proceed with that, you must have to develop with the Schrödinger-Poisson simultaneous equation. So it is the framework that you can play around, that your nanowire or quantum dot FET, you need to have a Hamiltonian for that. So the point is that you have a potential profile, then you need to have the Hamiltonian, then you will get the real time. You need to convert it to mode space. If you are interested, the references of my group or our is given here. And the pioneer of this domain modeling was Supriya Datta from Purdue University. You can read his book as well. And then if you convert it to mode space, then different types of parameters like self energies and eigenstates you have to calculate. But you may have to other parameters like you have to model the contact, because contact in the nano era of MOSFET is very crucial, because you have to come out of the concept of contact, ohmic contact. This contact will be no more ohmic, because whenever a nano or quantum scale is getting in contact with another one, say for example, a silicon quantum wire will touch the gold or aluminum or titanium metal, that is also of quantum scale. So those materials no longer continuous in terms of energy states. So their energy will also be discretized. So there will be a mismatch of the energy state between the metal and the semiconductor. So all these things will have a barrier height. So the thing is that whenever you are applying a voltage, those eigenstates will must have to align to transfer the charge. And when there will be aligned, the current transport will be totally controlled by resonant tunneling. So the concept of ohmic contact will be a bit different in such things. So therefore, contact modeling itself is very interesting and very challenging. one of my students' PhD is totally developing this contact modeling. And then, as you understood that strain is going to be an inevitable phenomenon in the coming years, so therefore strain incorporation, another route you have to create, and then you can think that you have to have a coupling between you have to think that your source, channel, and drain is the sink, source is the reservoir, and channel is the passage. So you have to calculate the coupling between the source and the channel, and the coupling between the channel and the drain. And you have to think also about the phonon scattering, because at that ultra low scale, all these phenomena will change its character. And therefore, whenever you will incorporate all these things, then you come to have the solution through the formulation of non-equilibrium Green's function. Once you get it, then you can calculate the density of states and then the charge distribution, then put it in the Poisson solution. You can calculate the potential. You can compare it. It's an iterative route. It is homemade from ourselves. Once you get the current transmission coefficient, you can calculate the current. Either you can get the potential, you can calculate the capacitance. So that is the main things, the entire modeling that we have to deal with in the current MOSFET at nanoscale with this one. I'm not going to read it, that how the memory architecture is also going to change, because it is directly related to the MOSFET operation. So I am going to end here, and thank you for your patience and interest. I'm stopping here. Thank you very much.
Thank you, sir.
Thank you.
Participants,
Thank you.
is there any queries? Dear participants,
If you have any queries, you can also mail me. I will answer through mail. No problem.
okay.
Yeah.
Shubhra ma'am.
There is a hand rising up. There is a hand rising up. Ranodip or Randip Kaur. Randip Kaur. Yes,
And
please.
yeah,
Randip.
yourself,
Randip.
you can,
Randip is raising his hands. Randip, please. I don't know whether he is present.
no, I think by mistakes he's that was
Maybe.
on.
Maybe.
Okay.
Okay.
Okay, Shubhra ma'am, kindly continue.
Yes, sir. Thank you. Thank you, sir, for your valuable presentation. And now, as we conclude this insightful session, it's my privilege to extend a heartfelt vote of thanks to our esteemed speaker, Professor Shonatan Chattopadhyay, for sharing his profound knowledge and expertise with us. Your deep insights, sir, into semiconductor technology and nanoscience have truly enriched our understanding, and we are grateful for the time and effort you have dedicated to this session. Once again, thank you, sir, for your invaluable contribution. We look forward to continued learning and collaboration in the future. And wishing everyone a wonderful evening ahead. Thank you very much.
Thank you very much. Thank you all. Good night.
Thank you, sir. Good night.
Thank you.
Thank you, sir. Good night.
Good night. Good night.